Hi, everyone. So I just wanted to finish up the notes from today, which what we didn't have time to quite do was talk about Lewis acids and Lewis bases and how they relate to Bronsted acid, Bronsted base, and just general acid-base chemistry overall. And what I would initially say is just that Lewis acids and Lewis bases are all talking about electrons. So Lewis acid is an electron acceptor, Lewis base is an electron donor. And in organic chemistry, we're all the time trying to get a handle on what's happening with the electrons. So often Lewis acid, Lewis base, understanding these terms and thinking about normal acid base chemistry is in terms of where the electrons are is usually the way to think about things. So concentrating on the electrons is really important. So a Lewis acid is an electron acceptor, um, and that includes so a Bronsted-Lowry acid would also be a Lewis acid. So this includes Bronsted-Lowry acids. So in this case, a Bronsted-Lowry acid would be HA, and in an acid-base reaction, a base will deprotonate the Lewis or Bronsted-Lowry acid to form BH plus A minus, and in this equation, HA was both a proton donor, so that's the Bronsted-Lowry acid definition, and an electron acceptor. It accepted electrons from B, and B, those electrons made the new bond to H. So that's what's happening with the electrons. And often Lewis acids and Lewis bases are the easiest terms to relate to nucleophile and electrophile. So electrophiles love electrons. That's what electrophile means. So Lewis acids are electron acceptors, so they are going to be electrophiles. Lewis bases are electron donors. They're giving away electrons to an electron acceptor. Electrons are negative. They flow to positive charges. So Lewis bases are nucleophiles. They love nuclei, so they donate their electrons to nuclei. So that's what a Lewis base is. Where Lewis acids can include Bronsted-Lowry acids, let me change that to can include Bronsted-Lowry acids. Lewis bases include all Bronsted-Lowry bases. So if something is a Bronsted-Lowry base, it's also a Lewis base. It's Bronsted-Lowry base is defined as something that accepts a proton. How does a Bronsted-Lowry base accept a proton? It accepts it by donating its electron pair to that proton. So any Bronsted-Lowry base is also a Lewis base. So next on your sheet, we have something where it says BH3 with water. So BH3, this is the Lewis structure, and it's important to note here that boron does not have a lone pair. So boron is lacking an octet, and because of that, it's going to be sp2 hybridized. So it's sp2 hybridized. And that makes it trigonal planar. So we've kind of drawn it trigonal planar here. We can see it's kind of a triangle. But we can also take that triangle. So I guess in regards to that triangle, where is the p orbital? The p orbital would be in front and behind the board. So we can take this triangle and turn it sideways. So we're rotating it from this direction to this direction. And when we do that, it takes the it takes the p orbital from being in front of and behind the board to being in the plane of the board. So this is BH3. It has an empty p orbital, which means it can accept electrons. So we'll write that here. BH3 can accept electrons in its empty p orbital. So if it can accept electrons, this is a possible Lewis acid. So we said BH3 with water, so let's draw water in here. Water has two lone pairs. It's a potential base. It can accept protons. It can also, when it accepts protons, it's donating its electrons. So it's an electron donor. So a reaction of H2O with BH3 would form this complex where the oxygen is positively charged and boron is negatively charged, but together it is neutral. So this was the Lewis acid. This was the Lewis base. And we can also say in this reaction, water was the nucleophile. Water added its electrons to the nuclei of boron. This was the electrophile. So that is kind of the definitions, Lewis acid, Lewis base, and how they relate to electrophiles, nucleophiles. And we see that they, while water is a Lewis base here, we wouldn't be able to define it as a Bronsted-Lowry base, but water is also a Bronsted-Lowry base in other situations where it would be taking a proton. Yeah, so you can fill in the next part in the above reaction was the nucleophile electrophile, was Lewis acid, Lewis base, and then the next question is, was there a Bronsted-Lowry acid or base? In this specific reaction, there is no Bronsted-Lowry acid or base because nothing's happening with a proton. Water can be a Bronsted-Lowry base, but in this context, it is just a Lewis base. So that should be everything you need for that sheet. And so why do we care about the Lewis definition? We care about it because, like I said at the beginning of the video, in organic chemistry, we're really always trying to track the electrons. And the Lewis acid-base definition is really a more inclusive definition where we can relate other reactions that are not just simple proton transfers to acidity and basicity through this Lewis definition. So it might kind of just seem like one more additional piece of definitions, and it kind of is that, but it's important that we're always thinking about where the electrons are. So that's the really important thing to think about. All right, I'll see you later.